Hello viewers, in the last session we have defined an essential singularity and we defined it to be the behavior of a function which is analytic in a neighborhood such that its limit as z goes to that singularity does not exist, okay, due to the reason that either there are two sequences in the neighborhood, in any neighborhood of that point, which go to which take f to different limits, or one of them goes off to infinity and the other goes to some finite limit. Okay. And we also claim that we will show that a more complex behavior is exhibited by a function in the neighborhood of an essential singularity. Okay. So, in this direction we will see the Casorati-Weierstrass theorem, which says that the function f assumes or comes arbitrarily close to every complex number in a neighborhood, in every neighborhood of an essential singularity. Okay. So, that is the statement. So, let me write that down, Casorati-Weierstrass theorem. Let f be analytic in B prime A R, that is in a deleted neighborhood of A, okay, and f comes arbitrarily close to any complex number. So, emphasis on any complex value, okay, in every neighborhood of A, okay, where A is an essential singularity. Of f. So, if A is an essential singularity of f, then f comes arbitrarily close to any complex value in every neighborhood. So, it is a very strong kind of description of this behavior, okay, and we will see a proof of this fact. Okay. So, let me remind you how we defined this. So, emphasis on any complex value, okay, in every neighborhood of A, okay, where A is an essential singularity. Of f. So, if A is an essential singularity of f, then f comes arbitrarily close to any complex value in every neighborhood. So, it is a very strong kind of description of this behavior, okay, and we will see a proof of this fact. Okay. So, let me remind you how we defined this essential singularity. Okay. Here is the slide from the last lecture. So, conditions 1 and 2, neither of them should hold, which means there is no alpha for which 1 holds, nor is there a alpha for which this other second condition holds. Okay. So, that is an essential singularity, okay, and we are going to use that. So, suppose that the conclusion is false. Okay, i.e., f does not come arbitrarily close to any complex value in every neighborhood. Okay. What that means is there is a complex number capital A to which f does not come arbitrarily close. Okay. So, there is a capital A and a delta. Okay. So, then there exists a capital A belongs to C, okay, and a delta positive, okay, such that the modulus of f of z minus A is greater than or equal to delta for every z in some, okay, in a neighborhood of A. So, for every z in a certain neighborhood of A. So, that has to happen because, so what that means is it does not come arbitrarily close to A, the complex value A. Okay. So, then this implies that for any alpha less than 0, okay, limit z goes to A, modulus of z minus A power alpha times modulus of f of z minus A. Okay. So, we are using the condition 2, okay, on, well, before I use the condition, let me say that this is this has to be infinity. Okay. That is because z minus A power alpha, when alpha is negative, okay, tends to infinity as z tends to A. Okay. And your f of z minus A is bounded away from 0. Okay. It is a positive number, it is greater than or equal to delta in modulus. Okay, in modulus. So, you have a non-zero number in the numerator, okay, divided by z minus A power alpha in modulus, okay, and then so that has to go to infinity. Z minus A power alpha in modulus goes to infinity. Okay. So, this is infinity, that is easy. Okay. Hence, A is not an essential singularity by the definition of essential singularity. Okay. Hence, A is not an essential singularity of the function f of z minus A, right, because condition 2 is satisfied. Let me go back to that condition 2. Condition 2 is satisfied for f of z minus A, okay, not for f of z exactly, but f of z minus A. So, we will see that this leads to a contradiction. Okay. So, so then there is implies there exists a beta, okay, can choose beta to be positive, because we have seen that there is an integral divide point. Okay. If condition 1 holds, then 2 holds, and if 2 holds, 1 holds. Okay. I am talking of the conditions that I have just shown, okay. And there is an integral divide point where condition 1 will hold to the right and condition 2 will hold to the left on the real line. Okay. So, there exists a beta can choose beta to be positive, because yeah, I mean that integral divide, beyond that integral divide you can choose a positive number. Okay. So, can choose beta positive such that the limit as z goes to A, modulus of z minus A power beta times modulus of f of z minus A is equal to 0, because that second condition holds, the first condition also holds. Okay. So, since 0 less than or equal to modulus of z minus A power beta times modulus of f of z minus modulus of A is less than or equal to modulus of z minus A power beta modulus of f of z minus A. So, I am using the triangle inequality on this stuff here, f of z minus A in modulus, okay, that is greater than or equal to this thing here. Okay. So, I am using triangle inequality in one form. Since that is true, the limit as by the sandwich theorem, the limit of the quantity here goes to 0, and this is a 0 anyway. So, the limit as z goes to 0 of the modulus of z minus A power beta, the modulus of this, okay, times modulus of f of z, okay, minus modulus of z minus A power beta modulus of A. Okay. So, I am multiplying modulus of z minus A beta into the modulus, okay, and then the modulus of this. A is equal to 0. So, I am taking the quantity in the middle and multiplying that out. Okay. So, then this implies that the limit as z goes to 0 of a certain quantity, complex quantity or a real quantity is equal to 0. So, the quantity has to be 0 in the limit. So, the limit as z goes to 0 of modulus of z minus a power beta modulus of f of z is equal to limit as z goes to this is a, I apologize, this is limit as z goes to a modulus of z minus a power beta modulus of a. Okay. And beta is positive, and we know that a is a fixed complex number, which we assumed f does not approach closely in a neighborhood of little a. Okay. So, a is a fixed complex number. So, this limit we know is 0, right, because beta is a positive quantity, z minus a goes to 0 as z goes to a. So, this is 0. So, what this implies is f. Okay. So, this now in the limit is equal to 0. What that says is that f does not have a is not an essential singularity of f, because condition 2 held for a certain beta. Okay. A is not an essential, the condition 1 held for certain beta, not an essential singularity of f. Okay, that is a contradiction to our assumption that A is an essential singularity. So, that cannot happen. So, f comes arbitrarily close to every complex number, okay, in the neighborhood of an essential singularity. Okay, so, that is the Casorati-Weierstrass theorem. We will look at some examples of an essential singularity. E power 1 by z, for example, has an essential singularity at z equals 0. Okay. Of course, it is not defined at z equals 0. Okay. So, this is analytic in B prime of 0, let us say 1, okay, in the deleted neighborhood of in a deleted ball of radius 1 centered at 0. Okay. And you notice that when you take z equals minus r I for some real number r belongs to r, okay, then what you get is and limit z goes to 0 will mean that limit r goes to 0. Okay. Limit z goes to 0 of this quantity, what will that be? Well, firstly, what is E evaluated at such a z minus r I will give you e power 1 by r times I. Okay. And this quantity, whatever this is, 1 by r is a real number. So, this belongs to unit circle, i.e., it has modulus 1. So, it stays in the bounded complex plane, that is the point. Okay. Whereas, if you take z is equal to a real number r, okay, then as z goes to 0, r goes to 0 and e power 1 by r, okay, this is 1 by r is arbitrarily large. Okay. So, e power 1 by r is also it is a real number, okay, and this is arbitrarily large. Okay. So, whereas when you approach along one direction to 0, namely from the negative imaginary axis to 0, your e power 1 by z stays bounded, it stays on the unit circle, whereas when you approach 0 from the positive real axis this way, okay, you see that e power 1 by r is unbounded. Okay. So, at least we can conclude that the limit as z goes to 0 of e power 1 by z does not exist, okay, and that will immediately give us the fact that it is an essential singularity, okay, because that condition 1 or 2 which we gave earlier will not hold, okay, and so it is an essential singularity. And by Casorati-Weierstrass theorem, we know more. We know that e power 1 by z now comes arbitrarily close to every complex number in every neighborhood of 0. Okay. So, that is an example of essential singularity. So, 0 is an essential singularity of e power 1 by z. So, that is a discussion of poles and singularities, and of course, we also discuss removable singularities, okay, which are the only 3 kinds of isolated singularities. And we have seen the dual behavior of zeros and poles and how they are tightly knit. We also gave a lemma in that connection, and that sort of wraps up our discussion about isolated singularities. Okay. So, the viewer should also be aware that there are non-isolated singularities. A function can have non-isolated singularities. So, non-isolated singularities, I will give you an example. We will not discuss them at length, but there can be such. Sin z has zeros at k pi. Okay. So, if I consider cosecant 1 by z. Okay. So, firstly, yeah. So, cosecant z has singularities. Okay. Or okay. Actually, we saw that it has simple poles at k pi, k not equal to 0. Well, at k pi indeed, okay, at k pi. And so, cosecant 1 by z, when you consider cosecant 1 by z, these this has simple poles at 1 by k pi. There are infinitely many 1 by k pi's, okay, in any b prime of 0. Okay, that is what I want to say. So, essentially 0 is definitely a singularity of cosecant 1 by z, okay, and in every neighborhood you have infinitely many singularities of cosecant. Okay. So, 0 is a limit point of these singularities. Okay. So, it is not an isolated singularity. So, 0 is a singularity of cosecant 1 by z, okay, and it is not isolated. As there are, as every neighborhood of 0 contains, okay, infinitely many 1 by k pi's, okay, which are all again singularities of cosecant 1 by z. Okay. So, there are non-isolated singularities as well, okay, but we will confine ourselves to isolated singularities, and they can either be poles or essential singularities. Okay. And the removable singularities are a peculiarity. They sort of can be forgotten in the sense that you can always extend the function to be analytic at that point itself. So, it is sort of a fake singularity. There is lack of information about the function f at that point, and when you have that information, the function can be made to be analytic. Okay. So, that is a discussion about singularities, and the following terminology is often used. A function f, okay, is said to be meromorphic on an open set G contained in C, okay, if f is analytic, okay, on G except for finitely many poles. Okay. So, if in an open set f contains finitely many poles, then you call f to be a meromorphic. So, that is a terminology which is often used, and okay. So, now what I am going to do is consider a different discussion. Okay. Since we know that 1 by z minus a squared, okay, has an antiderivative on let us say c minus a. Okay. We know that the integration of over gamma of 1 by z minus a squared, we saw this dz, okay, is equal to 0. Okay. Whether or not a is on the inside of gamma, I should say that gamma is a simple closed curve. Okay. So, so that gives independence of path, in the sense that path when you integrate 1 by z minus a squared in C minus a. So, here is a point A, let us suppose. So, it does not matter whether you integrate 1 by z minus a in this fashion. Okay. Here is the curve gamma, okay, and then I mean now this is a different gamma. So, I should probably say this is alpha, okay, or whether you integrate 1 by z minus a squared around some other path beta, oriented path, okay, beta. So, because the integration around alpha or beta minus alpha or alpha minus beta of 1 by z minus a squared dz is equal to 0, the integration on alpha of 1 by z minus a squared dz is equal to the integration around beta of 1 by z minus a squared dz. Okay. So, we saw that when that happens because 1 by z minus a squared has an antiderivative in C minus a. Okay. So, although we know that 1 by z minus a squared is not actually analytic inside of this curve gamma. Of course, at a it has a double pole. Okay. So, now the question is when does a function have an antiderivative, okay, or when is the integral of a function f of z dz, okay, is equal to 0, okay, whether or not f is analytic inside of gamma. Okay. So, we will only allow f to have isolated singularities in case it skips to be analytic inside of gamma. Okay. So, we will avoid non-isolated singularities for this discussion. Okay. So, now we will see that a function f, okay, will happen to have a antiderivative, okay, when we write f as a certain power series, as a certain double series actually, sorry. Okay. So, we will now write f locally as n goes from minus infinity to infinity. We will see what all this means of a n times z minus a power n in a neighborhood of a, whether or not f is defined at a. Okay. And we will see that the coefficient of z minus a power minus 1, okay, the coefficient of this decides whether f has antiderivative okay, in a neighborhood of A. Okay. So, that we will see. Okay. And this kind of series is a double series. So, we have to introduce what that means, and then the motivation for this is clear. We know that 1 by z minus a does not have a single valued function, okay, to which it is a derivative in a neighborhood of A. Okay. After all, we know that the integral of this is not 0, it is actually equal to 2 pi I. Okay, that is the fundamental integral when gamma is a circle of radius r. Okay, gamma star is a circle of radius r around A, which goes, I mean, when parameterized, it goes around once. Okay. So, this is in the positive direction. So, this is 2 pi I. Okay. So, it is non-zero is the point. So, 1 by z minus a is not the derivative of a single valued function in any neighborhood of A. Okay. So, there is a resistance there, okay, and hence 1 by z minus A fails this condition. Okay. And we will see that when we can write f of z locally like this near a singularity A, okay, it is the coefficient of this 1 by z minus A really which matters. Okay. And if that coefficient is 0, we will see that f is the derivative of a single valued analytic function in the neighborhood of A, or in other words, it has an antiderivative. Okay. So, for that we will need some machinery. So, in particular we are going to need the Laurent's expansions. Okay. So, in an annulus. Okay. So, first let us examine the case of a pole. Okay. So, if f has a pole, okay, of order m at A at a point A, okay, and is okay. So, I should have said this, let f be analytic in B prime A r. So, it is analytic in a deleted neighborhood of A, okay, and if f has a pole of order m at A at the point A, what we can do is firstly we know that then z minus a power m f of z, okay, this has a removable singularity at the point A. That is because we know that when you have a pole of order m at A, the limit as z goes to A of z minus a power m f of z is non-zero quantity. It is a complex number which is non-zero. Okay. That is when you say that it has a pole of order m. Okay. So, if you jack up the power of z minus a bit, so if you take m plus 1 of f of z, that is equal to 0. Okay. So, that condition will tell you that z minus a times this function, this z minus a power m f of z in the limit is equal to 0, which means you have a removable singularity for this function at z equals a. Okay. So, right, that is the condition, recall removable singularity okay, if and only if limit z goes to a z minus a g of z, let me say, is equal to 0. Okay. So, in this case the function g under consideration is z minus a power m f of z. Okay. So, this condition is telling you that limit z goes to a z minus a times z minus a power m f of z. Okay. So, this is the function g written here okay, that is equal to 0. So, so that has a removable singularity. This function has a removable singularity. Okay. So, now you redefine, you define a new function h of z is equal to z minus a power m f of z for z belongs to b prime a r, okay, and this is limit as z goes to a z minus a power m f of z for z equals to a. Okay. So, you define this to be the this limit at that point, so that you can remove the singularity. So, h is the analytic extension of z minus a power m f of z. Notice it is the analytic extension of z minus a power m into f of z, not of f itself. Okay. So, it is an analytic extension of this function. So, on b a r. So, what you can conclude is h has a local power series expansion at a, because it is analytic. Okay. So, by Taylor's theorem, you can write h as a power series. Okay. So, h of z is equal to h of a, okay, plus well, I will suppress h etcetera. Okay. So, I will just write C naught plus C 1 times z minus a. Okay. We know what these coefficients C naught, C 1 are. They are in terms of the derivatives of h, okay, and then plus C 2 times z minus a square etcetera, plus on. What is important is we also have a C m minus 1 z minus a power m minus 1 plus C m z minus a power m plus so on further. Okay. For z belongs to b a r. Okay. So, then let me substitute h of z is equal to z minus a power m f of z, okay, where I will not allow z to be a, okay, except at the point a. If I substitute z minus a power m f of z is equal to h of z, what I get is C naught plus C 1 z minus a plus C 2 z minus a squared plus so on plus C m minus 1 z minus a power m minus 1 plus C m z minus a power m plus so on. Okay. For z now belongs to b prime of a r, which implies f of z is, so I will divide by z minus a power m, because z now is not equal to a. Okay. So, f of z is C naught by z minus a power m plus C 1 divided by z minus a power m minus 1 plus etcetera m minus 2 plus so on plus C m minus 1 by z minus a plus C m by, sorry, just C m plus C m plus 1 z minus a plus so on. Okay. So, this portion, okay, looks like a power series. Okay. It has coefficients C m plus C m minus C m plus 1 z minus a, C m plus 2 z minus a squared etcetera. Okay. So, let me denote that portion by f 1 of z, okay. And by the way, this is true for z belongs to b prime of a r. Okay. So, let me denote that by f 1. So, f of z is C naught by z minus a power m plus C 1 by z minus a power m minus 1 plus etcetera, okay, plus so on until C m minus 1 divided by z minus a plus f 1 of z. F 1 of z is analytic, okay, on B A R actually, okay, but we will only use the fact that it is analytic on B prime of A R. there is no singularity of f 1 at A. Okay. So, this is true for z belongs to B prime of A r. Okay. So, what we see is that on B prime of A r, f of z when it has a pole of order m can be written in this peculiar form. Okay, in this form where you have coefficients to z minus a to the negative powers until negative m, where m is the order of the pole. Okay. So, I mean you can say this is sigma n goes from minus m to infinity z minus a power n. Okay. So, n starts at minus m and goes on until infinity, okay. And then you have f of z can be represented in this form. So, this portion which is which has negative powers of z, okay, is called the singular part of f. Okay. So, C naught by z minus a power m, okay, plus C 1 by z minus a power m minus 1 plus so on plus C m minus 1 by z minus a is called the singular part of f. Okay, it is called the singular part of f in this kind of expansion. Of f about A as powers of positive or negative powers of z minus a. Okay. So, we see that by the uniqueness of part of Taylor's theorem. Okay. So, we saw that the power series representation of h of z is unique, the coefficients C naught, C 1 etcetera, they are unique. They are actually certain derivatives of this h itself. So, for example, C 1 is the first derivative of h at A divided by 1 factorial etcetera. Okay. So, we saw the uniqueness of the coefficients. Okay. That uniqueness boils down to the uniqueness of representation of f in this fashion. Okay. And this kind of expansion for a pole is called the Laurent series expansion for a pole. Okay. So, if a function is analytic in a neighborhood of A and it has a pole at A, then this expansion is called Laurent expansion. Okay. We will see more general scenarios, but okay. So, this is true. Okay. And I want to motivate okay, I want to consider the motivation I have given earlier. Okay. So, once again since the power series converge in the neighborhood of A, okay, so I am talking about h here. Okay. Since the power series converge in such a fashion that if you want to find the derivative of h, you can find the derivative term by term of these series, okay, and then take the summation. Okay. So, also the integration of h, okay, can be done term by term. Okay. And so, that boils down to integrating f term by term. Okay. So, what I mean by that is if gamma is a simple closed curve, okay, oriented in the clockwise, in the positive sense, counterclockwise direction, okay, oriented positively. Okay. So, gamma is a simple closed curve, I should say in B prime A r, okay, such that A belongs to the inside of gamma. Okay. If A does not belong to the inside of gamma, then there is nothing much to say because the integration is 0. Okay. Then what happens is the integral along gamma of f of z dz, what is that going to be? That is going to be, well, I just said that I can integrate all of these term by term. Okay. Well, if you consider f f1 to be I mean in this one, if you consider f1 to be analytic function. So, there are finitely many terms. Okay. So, let me integrate that that finitely many terms. The integration of this is going to be the integration of C 0 divided by z minus a power m dz over gamma plus etcetera integral over gamma C 1 divided by z minus a power m minus 1 dz so on plus integral over gamma of C m minus 1 by z minus a dz plus integral over gamma of f 1 of z dz. Okay. So, f 1 is analytic on and inside gamma. Okay. So, we know that this integral is 0. Okay. So, we know that this integral is 0. Okay. And we know we have already done the fundamental integral. Okay. The integration of 1 by z minus a power m is 0 except for when m is equal to 1. So, all these guys are 0 except for this part. Okay. And we know the integral of this when gamma is a simple closed curve oriented in the counterclockwise direction. Okay. So, the integration of that is 2 pi I. Okay. So, this gamma f of z dz is equal to C m minus 1 times 2 pi I. Okay. So, it is actually the coefficient of 1 by z minus a in this kind of expansion of f of z, which we are going to call Laurent's expansion. Okay. Which okay, the coefficient of 1 by z minus a tells you whether this integral is 0 or not. Okay. And when this integral over gamma of f of z dz is 0 for every gamma, okay, in B prime of a r, then we know that f has an antiderivative. Okay. F has an antiderivative. So, it all boils down to, for at least the case of a pole, it all boils down to whether C m minus 1 is 0 or not, in order that f has an antiderivative in B prime of a r. Okay. So, let us summarize this. So, I will summarize what we have done as a lemma. Okay. So, let f be analytic on and inside a positively oriented simple closed curve. Gamma, okay, except at a point A, okay, inside gamma, where f has a pole of order m. Okay. Then integral gamma f of z dz is equal to 2 pi I times C m minus 1, okay, where C m minus 1 is the coefficient of 1 by z minus a, okay, in the singular part of the expansion of f as powers of z minus a in the neighborhood of a. Okay. So, that is the summary. Okay. And if C m minus 1 is equal to 0, so not, I mean I can state it separately. If C m minus 1 is equal to 0, then f has, okay, or f is the derivative of a single valued analytic function in the neighborhood. Okay. So, it's identically equal to the derivative of a single valued analytic function in the neighborhood of A, okay. At least in the neighborhood so far as gamma is in that, that neighborhood is contained inside of gamma, okay, in the statement of lemma. So, it has an antiderivative. Okay. So, we will continue to develop Laurent series expansion, and we will see the Cauchy's residue theorem, okay, in the next session. I will stop here.